In this video I want to talk more about finding the areas inside of polar curves. In a number of cases, setting up the integrals that we need to do is straightforward, because if they're asking for the entire interior of a shape, a lot of times we're just going to be doing the integral from 0 to pi or from 0 to 2 pi. But if they just want us to find some section of the area inside of a polar curve, it's a little bit more challenging. We sort of have to pay attention to where our integral should start and stop. And there, we need to review some trig before we really get into how to do this. And so I want to remind you about how arc cosine works, and arc sine for that matter. So the deal here is, whenever you take the arc cosine or the inverse of cosine of something, remember what's happening. You're effectively inputting a ratio, and it's telling you the angle. In particular, it's telling you like the primary angle that causes you to have that particular cosine or sine ratio. But the super important thing to remember is that for any given cosine ratio, there are a lot of different angles that can have that cosine ratio. And so it's important to remember that if you take the arc cosine of something and get theta as the angle, negative theta is another angle that will have the exact same cosine ratio. And as a way of reminding you about that, imagine your unit circle. Imagine someone is asking you, what is the arc cosine of, let's just say 0.3, right? That means your cosine is 0.3. So that sort of happens when your x-coordinate is 0.3. So that's going to happen up here at an angle of theta, but it's also going to happen down here at an angle of negative theta. And so that's sort of why that happens. So if you have arc cosine of something, your calculator is going to tell you theta. You're going to need to know that negative theta is also an acceptable answer. But on top of that, doing plus or minus 2 pi to either one of these things will give you more angles that have the same cosine value. And as we're working with these areas, we need to be mindful of the fact that it could be any of those angles that actually starts or stops the region that we need to look at. It's really necessary that we look at the graph and we critically think about where it starts and stops to figure out what angles to use for our bounds. Arc sine is a very similar situation. The difference here is that, suppose that you're told that the inverse sine of, 0.6 is something. That means our y coordinate is 0.6. We could get an angle of theta, but that y value of 0.6 also happens over here at an angle of pi minus theta. Right, so when you're doing sine, you're going to have whatever your calculator gives you, and then pi minus that value as well. And just like I said above, it could be that plus or minus 2 pi. Right? So we could also have our pi minus theta plus or minus 2 pi. And we're going to really need to look carefully at our graphs to figure out which bounds we need to use. And so in the next two example problems, and if I do any further ones past that, we're really going to be trying to critically look at the graph and think about all this stuff to put together our proper bounds. So let's get on to those examples. Okay, so here I want to find the area within the inner loop of 3 minus 7 cosine theta. So I'm intending this as a calculator problem. We're going to use the calculator. We're going to sort of pull this all together. So the first thing you probably want to do, well, if you were even going to come up with this graph, you would have to use the graphing calculator to draw the graph. So if I do that now, I can tell, just as I hit graph right there, that this point right here, that point right there, is where theta is 0. And then the curve starts to draw going this way. Right? So if I want to find the area inside of here, I need to figure out the angle where I'm at that point so that I can sort of figure out my bounds for this thing, right? So figuring out that point right there, like the important thing about that origin point is that that's where the radius is 0, right? So if I know that the radius is supposed to be 0, I can solve, oops, not sine, cosine, I can solve this equation and figure out what angle would get me there, right? So I'll have 7 cosine theta equals 3. Basically means theta is going to be the inverse cosine of 3/7. So when I throw that on my calculator, I'm going to get, let's see, what was it? It was 1.128, right? So I'm suspecting that like if I follow this orientation, that point right there will be, this theta value of 1.128. So So the question then is where's the other one of them? Like if this is 1.128, then what did I effectively come from? Like if I want to start my integral here and go all the way around this thing, how will I figure out what that value is? Well, if you think about it, that's another place where the radius is 0. It's another place where I'm going to get this same inverse cosine. Because it's cosine, I can take my theta value and subtract 1, not subtract 1, but make it negative. I'll have negative 1.128. And so my suspicion is that, and it sort of follows what I've seen here so far, my suspicion is that this point back here was a theta value of negative 1.128. Then we would hit 0, then we would come back to positive 1.128. Something that you can do on your calculator is if you go into your window, you can actually change your theta min and theta max values to reflect those things, and when we hit graph, if you did it right, it'll draw just the section that you're looking for. And if you've done it wrong, it'll show what it graphed instead. So if I take these theta values, I can now set up the integral to find this area inside. Right? I want to do the integral from negative 1.128 to 1.128. Remember, it needs to be 1/2 times that, times my radius, which is 3 minus 7 cosine theta, squared d theta. And practically speaking, when you do this on a calculator, you're probably going to have this stored as your R1, and so as I'm punching that into the calculator, I'm actually using R1. These values here I actually did as negative a and positive a because I'd stored them on my calculator. So remember all those things that we already know about how to do this stuff properly. I'm going to get 9.324 or 9.323 if you just truncated your answer. But great, that's my area. Especially in problems like these where you're doing so much thinking, I really think it's valuable to think about whether that answer makes sense, right? This region that I had here, as I sort of radiated outward and calculated this whole area, doesn't make sense that has an area of about 9. I would say so. This region here is 4 units wide. It's almost 4 units tall. And so a square that's 4 by 4 would be 16. And you could reason that this is about half of that overall square. An answer of 9 makes sense. If you had come up with 2 or 3, nowhere near enough. If you had come up with an answer over 16, way, way too large. So I definitely think it's important that you keep your wits about you and pay attention to whether your answer makes sense. In this example, I'm going to propose another method of trying to figure out the bounds of integration. So this problem is going to feel a lot different from the previous one, so just make sure you have your wits about you and your calculator by your side. So in this one, we want to find the area of the outer loop. So I want to find the area inside of the outer loop, but outside of the inner loop of this thing. So this is going to be a little bit complicated. We're going to start by just trying to find the area inside the whole thing, and then we'll go back and sort of cut out this part later. So we still need to find out this point right here. We need to figure out what's going on right there. That still amounts to where the radius is 0. It still amounts to me solving 0 equals 2 minus 5 sine theta. But rather than sort of solve that by hand and then use the calculator to do the inverse sine of 2/5, what I'm going to do instead is I want us to sort of really leverage the calculator to do that. Before we do that, you really should graph this thing in polar mode. So on your calculator, graph it in polar. Make sure that your window is set between 0 and 2 pi. And when you graph it, you'll notice the thing you want to look for is where does the graph start and stop. This point right here clearly represents 0, and then the orientation goes this way. So it starts out here, goes all the way around, and ends up back here again at 2 pi. The question is, how do we start and what is that point? Right? So what I'm going to do is I'm going to graph this. I'm going to graph 2 minus 5 sine theta, but not in polar. I actually want to go into our y equals, go into function mode, and graph this as 2 minus 5 sine x. And let's look at that graph. Okay, so here's the graph of y equals 2 minus 5 sine x. And this next part is super, super important. I really feel like these problems can be greatly simplified by understanding what I'm about to say. The important part is that anywhere that this function hits the x-axis, anywhere that this function is effectively equal to 0, is a different version of that point, is a different time that we hit that point again. right? And so what we can sort of figure out is we can say, okay, well, at time 0 we started here. That's this function being at that point. Then very quickly we hit a point where I started at this region, right? And so what we recognize is that basically between this point and the next time that we hit it, we are drawing out the inner loop of this thing, right? Then, between this point and this point, we must be drawing the entire outer circle. And it's actually really interesting. We know that we get right back to here at 2 pi, like 6.28. 6.28 happens right in there. And you can see that just past that, we get back to 0 again. Right? And so what we sort of recognize here is, hey, if I want to find the area of the entire thing, I should take the integral between this theta value, x value, and this theta value, or x value. Right? But when I do that integral, think about what it's going to get me. It's going to get me all of this area. And as it's doing that, it's going to get me all of the red area inside of here also. So what I'm effectively going to need to do is I'm going to need to do some sort of a blue integral to get the entire outer thing. Then I will have to subtract off some smaller red integral to take out all of this area inside of here. So I'm hoping that you guys, based on what I've said so far, can figure out what the bounds should be for the blue integral and the red integral as well, using your calculator to do that. So I'm going to ask you to pause the video, find these zeros on your calculator and sort of set up these two integrals, and then we'll check in after that. Okay, so what I found was that the blue integral started at 2.730, and again, on my calculator, I'm actually going to store that value. So I'm using 2.730, and then it ended at 6.695. As for the red region, I found that it started at 0.412, and it ended, well, I mean, coincidentally, it's actually going to end at the same thing that the blue one started at 2.730. Right? So now what do we need to do to set up these integrals? We still need the half out front, and we're using our 2 minus 5 sine theta squared inside of our integral. And so for this one as well, you'll have your 1/2, you'll have your 2 minus 5 sine theta squared d theta. So now we can run through and compute those two separate integrals. So I found the area inside the blue curve to be 46.456 minus the area inside of the inner loop to be 5.380. So all I have to do now is subtract those two things. So we can do this minus this. And I'm ending up with a total area, so that we're looking now at the area inside of the outer loop, but outside of the inner loop, being 41.076. Okay, so I know this was a long problem, but these problems, I really feel like going to the graph and using it to pick apart what those x-intercepts are and using those as your theta values is a really slick way to get through these problems. I think a final thought that I had before concluding this video, it's important that you be critical about your work here. Like, you really need to be paying attention to what you're doing, and every step along the way sort of asking yourself, is what I'm doing here right? Am I finding the right angle? Am I setting this thing up in the right way? And I think if you go through these problems and think about each step as opposed to kind of just blindly trying to set up integrals, I think you'll have a lot more success.